And thanks for joining me today. We're going to be talking about fairness and the application of fairness within machine learning prediction algorithms. And specifically, we're going to be talking about a framework that uses causal networks to establish counterfactuals. So let's get started. So we're going to divide this basically up into four pieces. So we're going to talk about the prevailing definitions of fairness, what's in practice now in terms of law and machine learning. Um, Move over to causal networks as a framework to establish deeper, more interesting questions about fairness, and use that to establish what is known by Kozner as counterfactual fairness. What is it? How do we accomplish it? And what does it mean? We'll have a short discussion at the end. So fairness. What does fairness mean? Um, there's multiple definitions of fairness, um, not one single definition. And we're going to talk through three definitions here that have some prevailing use in um, machine learning and legal settings at large. So the first definition that we're going to talk about is unawareness. Um, when we define unawareness, that means that we've dropped this protected class, this notion of, for example, race or gender, um, something that would have protection under discrimination law, that we've just dropped it as an attribute. So it's a procedural move. It's not even part of establishing our prediction procedure. It's basically a data step. So it's common in legal settings. Um, it's attractive because it's clean and very, very simple. It's not so attractive in that it's very easy to substitute a correlated variable and launder this notion of race or gender through that. So an example is Oakland predictive policing, Oakland, California, where I'm from. Predictive policing is not allowed to use race as an attribute, but neighborhood, due to historic redlining, definitely has that strong correlate with the race and ethnic minority status in the neighborhoods at large. The second prevailing one is demographic parity, and the idea here is that equal groups get equal acceptance rates. Um, and one notable thing right away is that if you had a perfect predictor, let's say you were doing hiring and you couldn't see the success outcome, but you had some sort of hiring rubric that gave you a predictor, even if you could completely tell the successful outcome at large, it's not possible for it to achieve demographic parity unless there's equal base rates in the population. This is, even despite that, this is a prevailing way that diversity, equity, and inclusion efforts are ranked. A third major way is equalized odds, and that's in statistical terms, the predictor is independent of the protected class, conditional on the outcome. An idea here is that the SAT could be an objective standard of success in college and would allow for equalized odds of success regardless of your membership in, for example, different ethnic communities. But it is subject to um, the exacerbation or at least maintenance of prevailing disparities between um, the success outcomes in multiple different groups. That's not the only reason the SAT was dropped in the UC system, University of California system, but it is a reason. Each one of these we can define mathematically fairly simply um, using our basic conditional probability terms. And that makes them easy to calculate and assess, easy to communicate. Um, they're very easily implementable in policy and code. But we can talk about the inadequacy of these. So they all have substantial critiques, not just these ones I've listed, but the other fairness definitions out in the wild. Um, they exist primarily because of, or at least in large part, due to convenience. They are easy to form and easy to talk about. They perhaps do not get at more philosophical definitions of fairness. Um, a thing that we should keep in mind is that they're fundamentally incompatible with each other. The impossibility theorem of fairness basically states that unless the base rates are equal, these measures can't all possibly succeed at the same time. But the most important thing that we want to bring in here is that there's a mismatch with the implicit fairness definition that we might use otherwise, that if we weren't looking at the metric first, but looking at the definition and our own use first. And that definition is grounded in counterfactuals, what-if questions. And these are fairly common in any sort of um, reasonable discourse around these problems. What if I were white rather than black? What if I were a man rather than a woman? These what if sort of questions are extraordinarily hard to answer if all you have is observed data and all you have is a probabilistic model. And so here we're going to extend our model to allow us to answer these sort of counterfactual questions in better depth. And so we're going to bring in, as our uncertainty framework, we're going to bring in causal networks. This is an extension of the Bayesian networks, both authored by Judea Pearl. But this is an extension with stronger assumptions that allows us to look at questions of causality. So here's an example causal network shown here that talks about police and their use of force in arresting minorities. And you can see a few things right away. It looks somewhat similar to a Bayesian network that we've looked at, but now has latent variables like this notion of suspicion here. There's a notion in causal networks that there's no correlation without causation, so that all of the latent variables need to be in play and all of the correlation should be explained structurally. There's noise heterogeneity terms that I haven't included in this one. They're normally omitted if they're uncorrelated. The most important thing here, though, is these arrows are no longer about conditional probability. They are causal links, and they have some sort of structured equation behind them. So if we are looking for what is this causal link between minority and stop, there's an equation that drives that home. So here's a more complete causal network. This one is actually the one of the two that are used in the Kushner paper about counterfactual fairness. Here, the assumptions that are built in that need to be backed up by other research, but the assumptions are minority status and gender affect causally the GPA scores, LSAT scores, and the first year success in law school. Here I've listed these noise terms, these latent noise terms, as well as a latent variable for knowledge that might impact all of those as well. And here's an example of these structured equations. Sometimes they're simpler than this and just straight linear equations, particularly in economics. Here we're seeing that they're relatively simple probability distribution functions that take into account each one of these variables as well as these kind of noise terms. And so this constitutes a causal network. So when we look at the structure of these causal networks, what does it have? Well, it has Bayesian network properties. This network induces a joint probability distribution from its very structure. So the notions of deseparation, chains, independence, those all are still there as a product of this. So formally, this is a causal Bayesian network. And here we can use those notions to talk about direct effects and whether conditioning on this stop either provides or doesn't provide us a way to look at the effect of minorities on the use of force. We can actually see multiple paths with an open V structure. So this is very similar to Bayesian networks that we've looked at before. A causal network, though, has stable links, and those stable links are a product of those causal structures that we just talked about. So it's not just observational data and conditional probabilities. These are mechanistic relationships between them. There's still an infinite number of possible, for example, structural equations here, but the arrow can only go one direction. There's a causal mechanistic link that's driving that. What this allows us, though, is the ability to do interventions, which in Pearl's language is called do calculus. And an intervention is really kind of playing God and changing the value of an observation. It's fundamentally different than looking at a Bayesian network where we might have evidence that update our probabilities. Here we actually come up with a different graph just by virtue of setting one of these variables. We can remove one of the arrows entirely and come up with a new graph and a new probability distribution. So that's a fundamentally different operation than what we could do before. And it also allows, that in turn allows us to look at counterfactuals. We can say, well, what would have been this outcome if we went back and changed this value? So that's a new capability that we get. So counterfactuals then have 3 steps. And it's kind of this notion of go back to the past, change something, and then rewind the clock. So this abduction step is the most important. Using that structured equation, we can actually come up with what these noise terms really were. So we know how we saw, why did we see those values that we saw before? And that will allow us to take the action of intervening and forcing the variable of interest to a new value. And then we can use that to do a prediction step. So kind of go back in time, change something. It's a little science fiction-y in how we do it. And we can only do it if we have this structure that allows us to see what else was in play that drove the results we saw originally. So counterfactual fairness is just combining this notion of causal networks with the notion of fairness. So we say the predictor is counterfactually fair if any sort of, and this is our intervention logic, if the counterfactual probability is the same, even if we do an intervention. So that's kind of what we would want it to be. If we went back in time and changed these values of race, for example, as a predicted class, that shouldn't change the predicted probability. And it's, definitionally, that's exactly what we would want to see from fairness. So in terms of our algorithm, we have this algorithm that we can establish. And this is really just that same counterfactual abduction, action, prediction step. Here we're establishing what those U values were using this causal model M. And that really is that abduction step. So here it's assuming we can't easily deal with this probability distribution. We're going to use Monte Carlo methods. And we're going to generate these points that we can use then to establish our learned algorithm. So that is very clearly just a capture of that Perl causal network counterfactual. And then we can get to design. The design is a little harder, but we use one fundamental property of this counterfactual, which is if we just omit A, all of the predicted class, and any of its descendants in a causal chain, if we omit them all, then it has to, any of our predictors will be counterfactually fair. So this is kind of the unawareness on steroids. But we're using now the causal network to choose which things to exclude. And it's got a few levels. We can just omit it. We can add some latent variables. We can make a fully deterministic model for each one of those variables, including some new latent terms. But in each case, we know that those predictors will end up being counterfactually fair. So in terms of the discussion here, I entered into this because I thought this notion of causal networks and causal inference and counterfactuals would be a silver bullet, that it would allow us to access questions that we couldn't access otherwise. I've come to, in this process of reading the texts, come to this notion that it's much more delicate than I thought it was. It's pretty hard to establish the causal model and the explicit assumptions, let alone defend them. And so that's much harder to you from observed data and do the identification step of the causal model. So that's not easy at all. And this notion that we're projecting into a fair world where we're kind of removing these aspects of race and gender in our outcomes leaves us with potentially making a fair decision that someone else is going to be now subject to without benefit. So the example of a loan in a fair way might still be harder for a minority to pay back due to the causal nature that we described in that causal model. So the payback of that loan, even if the decision to make the loan was fair, the payback is not necessarily fair and subject to all of these constraints in the causal model. So I left believing this is a useful framework maybe to evaluate alongside others and derive some information but may be hard to implement in practice. So thank you for your time. I appreciate your questions and feedback.